So today let's analyze a typical computer power supply from a scrapyard. Let's see if it failed or if it was scrapped just for obsolescence. Not sure what else to call it other than a crappy computer power supply. 350 watts, a basic one. Nothing special about it. It's just trying to look posh using the big fan. The cable has been cut. I decided to make a video about it because these are a bit nostalgic for me. 20 years ago, when I was a broke student, I fixed about 100, maybe couple hundred of these for about $4 or $5 a piece. And of course the only way to achieve this was that the student's time has no value and the spare components were taken from other power supplies which I couldn't fix. But now 2 decades later I'm very aware that my time is the most valuable thing I have. I really shouldn't waste it on some nonsense. But now let's open it and see the internals and see if there is a failure or if they got rid of it just because it was too low power for the application. It seems it's actually still sealed, but well, who would actually bother fixing these? And there is some dust in it. This is always an indicator of how much it was used. Many times I have seen a completely clean power supply which already failed, but I've also seen way dirtier ones. And you can immediately see how cheap this one is. The mains comes in here. Fortunately there is a fuse at least, but this interference suppression double inductor is omitted here. The capacitor here is omitted. The X capacitor, the Y capacitor is omitted. Of course the discharging resistor for the capacitor here omitted. There is no big bridge rectifier, just 4 small diodes. There is also a jumper here, and there was supposed to be a passive power factor correction. I guess this is from the era of passive power factor corrections before the active ones. And the passive power factor correction was much simpler. It was just an iron inductor in a series with the mains going in before the bridge rectifier, sometimes after it. It was partially correcting the power factor, not as good as the active one. It was heavy, big, required a lot of copper. Just some examples of these passive power factor correction inductors. They're basically windings on an iron core. They slightly look like transformers or fluorescent inductors. And they're heavy. One of these was supposed to be connected here, but it's omitted too. Then you have the NTC thermistor, at least this one is here. I have even seen some power supplies where even the NTC thermistor for inrush current limitation was omitted. Then these capacitors, they're 2 in a series for 220 to 240 volt mains. For 100 to 120 volt mains, these can be actually switched into a doubler circuit, but the mains voltage switch is actually omitted here too. This one is for 230 volts only, not for the 100 something volts mains. At least there is one Y capacitor here. It's basically the only interference suppression in the entire power supply, it seems. And there is this heat sink with transistors. You can see 3 transistors, 3 transformers, because this is an ATX computer power supply. In the even older AT computer power supply, there would be just 2 transistors and 2 transformers, because the AT power supplies didn't have the auxiliary power supply of 5 volts, or standby power supply, which was always on even in standby. AT computers didn't have any standby mode, only the main power supply, and they were typically switched using a physical switch disconnecting the mains, whereas ATX is switched by just a micro switch into standby. And in the AT power supplies, the half bridge was actually self-starting, using base 2 collector resistors on the transistors in the half bridge, whereas ATX is not self-starting. The control circuitry is powered using the standby power supply. Here you can see the main transformer, 350 watts. And this produces 12 volts, 5 volts and 3.3 volts, as you can see here. And some currents. And whether the power supply can actually supply these currents or it bakes itself when fully loaded, that was always a question. Some of these might have some negative low current output. And here's the standby power supply. And this one is the only one always on. The rest of it switches into standby and shuts down. Let's take the board from the box. It's on 4 screws. These screws also connect the board to the metal chassis and ground the output basically. The connection of the 0 volt output rail to the chassis is done by screwing these screws into it. And the board is out, and we can take a closer look at it. And on the other side of it, a little dirty, but I have seen much worse. It's basically a half bridge, which was the most common topology of these before the single switch forward and two switch forward ones came, are the MOSFET half bridges. This is a bipolar half bridge, 2 NPN transistors, not MOSFETs. And you can see this film capacitor in series with the primary of the transformer, the main one. And these are discharging resistors for these capacitors, 150 kilo ohms for each. This is a snubber network. This power resistor and this small capacitor, this in series is connected in parallel to the primary. And the typical thing about the half bridge with bipolar transistors is that there is a base driving transformer. And the control chip is actually on the secondary side. Controlling two transistors, they control the base driving transformer, and this drives the basis of the transistors in the half bridge. Whereas most other switching power supply topologies are using a control chip on the primary side. And the main transformer has some center-tapped secondaries, typically 2 times 7 turns for 12 volts, and 2 times 3 turns for 5 volts. And primary is typically 40 turns, sometimes 36 turns when using passive power factor correction, which dropped some voltage. The 12-volt double secondary is typically rectified using a silicon diode, an ultra-fast one, a double diode with a common cathode. Then it goes through an iron powder core inductor into the first parallel electrolytic capacitor, then through a small inductor, another parallel electrolytic capacitor, and to the output, the yellow wire. The same applies to the 5-volt rail, but the diode is typically a Schottky instead of ultra-fast, which has a lower voltage drop but also a lower reverse voltage rating. Then it goes again via this inductor, which has more windings, typically common for all the voltages, and then again an electrolytic capacitor, a small inductor, another capacitor, and the 5-volt output. In an AT power supply, these would be the only outputs, 12 yellow wires and 5 red wires. But an ATX power supply has extra 3.3-volt outputs, orange wires. And there are 3 main ways ATX computer power supplies were producing the 3.3 volts. One of them was just linearly dropping the 5 volts to 3.3 volts, but this was quite lossy. The second way was having a dedicated secondary in the transformer for 3.3 volts, 2 times 2 turns, and this going through another Schottky diode and another winding on this inductor, a capacitor, small inductor, capacitor, just like in the other outputs. But the disadvantage of this was that there was one regulation for all voltages, and the 3.3 volt output wasn't regulated super accurately, but it was more efficient than dropping it from 5 volts. And the third way of obtaining the 3.3 volt output is the one used in this power supply and probably the most common one. There is a regulation with a saturable inductor. It's a freight inductor with a core which can easily saturate, and thanks to this core a high current can be controlled using just a very small transistor with no heatsink. It's basically a magnetic amplifier, and this topology didn't have a separate secondary for the 3.3 volt output. It was using the secondaries for the 5 volts. And typically in one leg, but sometimes in both legs, it had the saturable inductor, occasionally 2 inductors for each leg. And here one leg of the 5 volt secondary goes straight into the 3.3 volt rectification double Schottky, one leg goes through this saturable inductor into the other half of this double Schottky, and from the common cathode it goes via a separate inductor. It's not common with the other outputs, and then it goes into a capacitor, small inductor, capacitor, and the 3.3 volt output, orange wires. And this inductor is again on an iron powder core. These are ferrite rods. It's not a complete magnetic circuit, so it's like a core with a massive air gap, but this one has no air gap. And the negative low current outputs, like -5 and -12 volts, typically also have a winding on this one, a thin wire. And in the newer ones, the -5 volt output is omitted, just a -12 volt one is present. And it uses this capacitor, this inductor, and this capacitor. Nothing winding on this. And it's just rectifying the 12 volt secondaries, but the other way, using some small diodes. And of course the base driving transformer controls the basis of the half bridge using series small electrolytic capacitors, which were a very common failure. They dried out, but also these capacitors failed often. These are typically the most common problems in these power supplies. But sometimes even the primary ones would fail, sometimes the half bridge, occasionally the control chip also failed. But in a lot of cases also the failure was in the standby power supply, which uses this transistor. Standby power supply is low power, so it's a flyback using this transformer. There's a power transistor, some auxiliary small transistor. In this case there is no chip in the small power supply, just a self-oscillating flyback with this transformer with a ferrite core with an air gap. And it's rectified using this Schottky. This goes into a capacitor, inductor, another capacitor, and produces regulator 5 volts. On the transformer there is a secondary rectifier using a small diode producing 12 volts standby, which doesn't go outside of the power supply, it's just to power the chip. And very often the transistor in this flyback power supply failed, but also this Schottky or the capacitor at the output. Sometimes there was a small electrolytic capacitor in the feedback, and when it dried out, the power supply went runaway. The output voltage was going up from 5 volts all the way to, let's say, 15 volts. The output electrolytic capacitors, typically rated for 10 volts, exploded, and it could cause damage to the motherboard as well. This was a horrible design, relying on the regulation with an electrolytic capacitor in it, which, if it fails, causes a runaway. But as far as I remember, the small electrolytic capacitor causing the runaway was typically on the primary side. You can see no small electrolytic one here, just the ones in the main power supply. And here's the optocoupler for the flyback power supply, the standby one. When the standby power supply transistor failed, it shorted, it typically destroyed several more components, the small transistor, the bridge rectifier, the fuse, maybe some diode here, and also exploded the current sensing resistor, the very low resistance resistor somewhere here. And the half bridge failing typically blew the bridge rectifier and the fuse too. If one transistor in a half bridge shorts, the other one also shorts, because it's switching into a short circuit basically. And also very often these rectifying diodes failed, they went short circuit. Often they overheated, and very often these screws were actually loose. These silicone pads over time compress. The components have a very poor thermal contact with the heatsink, and they overheat. This can apply to the transistors too. But a few times it took me a long time to find the problem in the power supply, and the problem was that somebody dropped it, and because the heatsink is heavy, it broke some of the pins of these diodes or these transistors, and this was the problem, and it wasn't easy to find because I wasn't expecting it. Also, a failing fan can cause everything in the power supply to bake itself. And of course the better power supplies not only had some interference suppression here, but on top of it some additional interference suppression mounted straight on the mains inlet connector. This is absolutely no interference suppression other than this capacitor going probably from the negative of the rectified mains to ground. But in this power supply I don't see any visual problem. No capacitors are bulging like this one. I guess everybody's screaming, try to power it, so let's power it. Putting it back into the box. And this one is an old school construction, but it's made in 2012. There are still no SMD components on the board. And I guess this ground wire was actually supposed to be separately screwed here. Not onto here, but they saved one screw. This one really went through some cost cutting. But now let's plug it in. Without connecting anything, it should produce the standby 5 volts when I plug it in. Or maybe explode, who knows. No explosion. The violet wire should be the 5 volts. There is actually 5.14 volts, nice. And the power supply should start when you connect the green wire with the ground or any black wire. So let's connect it. And the fan actually sort of moved, but didn't start. Let's measure the yellow wire, the 12 volt output. It produces about 1 volt and disappears. Does it just need a load, or I guess it's not working at all? It sort of tries to start up. The lamp is blinking, the fan is slightly moving. It makes a pulse when I connect the green wire and then it shuts down. It's better to check the primary capacitors for a charge before touching something. Is some of the secondary double diode is shorted. This is the 12 volt rail, and its voltage drop at low current, nice. And the other side, but of course the halves of the diode are connected with each other with the very low resistance of the secondary, so both halves basically show the same thing anyway. This is not shorted. The 5 volt rail, well, this shows a very low voltage drop, but it's probably some loading resistor, it's not a dead short. And the 3.3 volt rail, still not a dead short, I guess this also has to be some resistor loading it. Or maybe the 5 volt rail needs a load. No, just a pulse and shuts down. Sometimes when one half of the double diode is shorted, it still produces a short pulse at the output when it's trying to start up. In such case it's typically just half a volt or less. It wouldn't move the fan that much. And based on the measurements, these diodes are not shorted. I was going to check the ESR of the electrolytic capacitors in it, and it seems my ESR meter failed now. Nothing's connected and it's showing about 1 ohm. I tried changing the batteries in it and it didn't help. There are 2 double A's in it. Still the same after changing the batteries, and I was checking the capacitors for a charge before using this one. And it has a pair of anti-parallel diodes protecting the input anyway. Turning it off and back on, which doesn't work. Still showing the same. So I have to try using this to measure DSR. The minus 12 volt output capacitor is just 39 milliohms and 42 milliohms. The 12 volt rail 14 and again 14 milliohms. The 5 volt rail capacitor is 30 milliohms and 29. 3.3 volt rail 22 milliohms and 22. 5 volt standby rail capacitor is 54 milliohms and 43. These were all high capacitance capacitors, which should have a very low ESR, and they have. This one is the capacitor on the supply rail of the chip, 260 milliohms. It's a bit more, but it's a smaller capacitor, just 47 micro instead of several hundred or even 1000 micro. This is a very good ESR for it. Some small electrolytic capacitor here is 20 ohms. That's actually a lot. This small blue one, it's just 1 micro, but 20 ohms is a lot even for 1 micro. It should be about 8 ohms at worst. Or maybe this one is not properly measuring very low capacitance. It's like 1 micro, which is a low capacitance, almost the lowest you can get with an electrolytic capacitor. It sucks when you have to use tools you're not very familiar with. Now the pair of 10 micro electrolytic capacitors in the base driving circuitry, one is 6 ohms, which is also sort of high for 10 micro. The other one is about 3.6. Also the difference between two identical capacitors is a bit suspicious. Just for comparison, a new 10 micro capacitor is about 1.9 ohm here. Another 10 micro different type, 2.7. It of course differs from type to type. These three small electrolytic capacitors in it have a bit higher ESR, but it would still guess acceptable. It wouldn't prevent it from starting, especially with very little load. Typically when these were high ESR, it wouldn't run with a high load but still ran with a low load. Of course I can just try to change them if I'm desperate, but let's also measure some diodes in it. 0.6 volts small diode, good. Some bigger diode, 0.5 volts, nice. Here's a Schottky which at a very low current from this tester, about 1 milliamp, only shows about 0.13 volts voltage drop. Of course at a high current it would drop about half a volt, and these silicon diodes at a high current could drop almost 1 volt, but it seems most of these diodes are good. And the other way, I guess it has a resistor in parallel, but it's not that short. I desoldered one lead to test it properly, and it seems good. Of course I forgot to check the pair of diodes in the negative 12 volt power supply. Half a volt here, the other one half a volt. And here I'll have to show a close-up of some solder joints here. What the hell is this? This thing almost no solder. This one horrible. These pins here. There is almost no solder. Holes. This thing, this one. This is horrible. This is probably the absolute cheapest crap you could get in 2012. Amazing solder joint is here. At this point it could be easily just a better solder joint, couldn't it? But anyway, let's measure some transistors. Base 2 collector, base 2 emitter, good. Another NPN small transistor, base 2 collector, base 2 emitter, nice. That's these two transistors. What about this one? This is PNP, emitter to base, collector to base, emitter to collector, or collector to emitter. That was some diode in parallel probably. I tested these 10 ohm and 1 ohm resistors in the base driving circuitry. They're good. I tested basically all the relevant diodes, the ESR of all capacitors except the primary ones, of course. I should check them. 144 milliohms. 152, and of course you really have to check their discharge before testing them. You don't really see anything obviously wrong here. Of course the horrible solder joints, but they're making contact. Everybody's screaming change the small electrolytic capacitors. But also the 3.3 volt rail diode, the double one is suspicious a bit, but it's not possible to measure it in circuit very well. Let's actually cut this, and I disconnected its common cathode to measure it properly, and it's showing a nice voltage drop of a double Schottky diode. I reconnected it and I have to stress, I'm really analyzing and fixing this just for educational purposes, just to show how to find the problem and fix it. There is absolutely no point whatsoever fixing something like this. The worst quality power supply with the wires cut. I still don't see anything wrong here, except the higher ESR of these three capacitors. Am I actually going to start changing these capacitors? Well, maybe not yet. I guess I'm being an idiot here. Or maybe I've never fixed an ATX power supply before with the wires cut. But in the connector in it, there are actually some wires connected with each other. there is a feedback for the 3.3 volt rail, a thinner wire basically going to the same terminal as the thick orange one, and one thin wire going to the same terminal as the thick 5 volt red wire. These are supposed to be interconnected. You don't see any 5 volt feedback here, but this brown one is the feedback for the 3.3 volt rail, I guess. The feedback goes from the board all the way to the connector and back to sense the voltage after the voltage drop of the cable. Connecting the brown wire, the 3.3 volt feedback with one of the orange wires, and now the green with the black. And it's running. So there was probably never anything wrong with the power supply. I guess it was probably trashed just for obsolescence. But I really never had to fix an ATX with a cut connector before, so this thing didn't come to my mind. But it's a nice example that sometimes you have to look for the problem outside of the box. Literally. There's the 3.3 volt rail, the 5 volt rail, and the 12 volt rail. Testing it using a lot of lamps, and it's working. Interesting, the quality is as bad as it can be, and it's still trashed for obsolescence, not for a failure. The voltages are about right, 3.3 volts, 5 volts, 12 volts, minus 12, and the chip supply voltage 14.4 volts. And here's the switching waveform. One leg of the 12 volt winding is just about 32 kHz, quite low frequency. But of course bipolar transistors are slower than MOSFETs. The common cathode of the 12 volt double diode, it has doubled the frequency on it. One leg of the 3.3 volt Schottky connected straight to the secondary, and the other one connected via the saturable inductor. Quite a different waveform. And the common cathode of the 3.3 volt double Schottky. One half cycle is the full length, the other one is limited using the saturable inductor. This is the standby flyback power supply, the 5 volt secondary, 72 kHz. So that's it, because I didn't notice this, at least I could show you how to look for the bad component, if there was anything to fix, and if anybody needed to fix this, and also an opportunity to show some waveforms and explain how does it work. And if you like my videos, please consider supporting my channel on Patreon or using the thanks button, based on the value you receive from my videos. You can also subscribe, and big thanks to all of you who already support me, because this is what keeps my channel running.